Hello to my friends joining us via recording. We are starting our discussion of lesson number 4. So lesson number 4 is about the process of transporting things across the membrane, specifically the kinds of things that on their own wouldn't be able to get through the membrane. So my friends here in class with me today, I want you to help me out. We've done this before in class, so let me type our stuff for us here. We're going to do some coloring. So the parts of the plasma membrane that are hydrophilic, we're going to make those parts green, or excuse me, red. I was getting ready to do green. The parts of the membrane that are hydrophobic, we're going to make those green. The parts of the plasma membrane that are polar, we're going to make those blue. And the parts that are non-polar, we're going to make those orange. So do me a favor. Above your screen, there's that little pencil. Pick a color, red, green, blue, or orange. Help me start coloring in my membrane here. I want to remember which parts of the membrane are hydrophobic versus hydrophilic, which parts are polar or non-polar. We need to remember where things are. For a while, we just were really loving the hydrophobic color, but now I'm starting to see them all, which is perfect. Okay, so we're perfect. We're color coded. Here's what I want to point out, and I hope that by this point in our anatomy class, you are familiar with this. The words hydrophilic and the words polar, they mean the same thing. The parts of the membrane that are hydrophilic are also parts of the membrane that are polar. The parts of the membrane that are hydrophobic are also the parts of the membrane that are non-polar. Now, these two sets of words mean different things. So if I am hydrophilic or I'm polar, how do I feel about water? If I'm hydrophilic or I'm polar, what are my thoughts about water? Yeah, I love water, right? That's what philic means. I love it, or I play nice with water. So loves water or plays nice with water. So some parts of my plasma membrane, the parts that I would call hydrophilic or the parts that I would call polar, they play nice with water, or they like to be around water, essentially. But I have other parts of my membrane that are hydrophobic, which is a synonym, or it means the same thing as nonpolar. And when I talk about those nonpolar parts, or the hydrophobic parts, what are their thoughts about water? How do those parts feel about water? Yeah, they hate it, right? Or they don't play nice with it. They can't be around it. They can't stand it. We can see this when we look at the shape of the plasma membrane. My parts that don't play nice with water, that hate water, we said that they were going to be colored orange, or they're going to be colored this green color. Notice that my orange and green parts are here in the middle of the membrane. Remember, let's add this in here, that in the middle of the cell, we have water. Ooh, that's what happens when you press 0 with the shift key. Here we go. Try again. We got water on the inside, and we've got water on the outside. Water is everywhere in the outside of the cell. It also fills up the cell. The name of that watery soup inside the cell, again, what do I call that fluid in here? I'm just going to keep asking the same question because we need to make sure we know it, right? Yep, the stuff inside here, it's called my cytosol. Cytosol is made up of a bunch of water, lots of water inside. Water on the outside in my types of fluid that are called extracellular fluids. Remember, there are a couple of them. One of those extracellular fluids is called plasma. When I talk about plasma, Though that is a fluid that is outside of cells, but those cells are inside what? Where's plasma found? Inside of, yeah, inside blood vessels. Inside blood vessels. Plasma is the liquid of your blood. So some of my water outside the cells is called plasma. Some of it is called interstitial fluid. Interstitial fluid. That's the fluid that's found outside of cells that are found in tissues. Tissues like we're looking at in lab this week. So fluids on the outside of the cell, plasma, interstitial fluid, they've got water inside of them. Fluid on the inside of the cell called cytosol. These hydrophobic parts, or these nonpolar parts, they don't play nice with water. They can't even with water. So they squeeze together in the middle of the plasma membrane of the cell. And as they're here in the middle of the plasma membrane of the cell, there's no water inside of here. But I also have some parts of the membrane that do play nice with water. That's my polar parts. That's my hydrophilic parts. So I can see them here in red and blue in the very middle, forming the inside of the membrane and forming the very outside of the membrane as well. Remember that we talked about how this part of my membrane, these are called the heads. So we have the phosphate head groups that like to be around water. They're on the outside touching water. They're on the inside touching water. And then we have these hydrophobic or these nonpolar tails that are not touching water. So when we talked about the structure of the plasma membrane, we said that it all came down to the way things play with water. Some types of chemical compounds do like water. Some types of chemical compounds don't like water. And based on that, we get this structure where the membrane is called the phospholipid bilayer. The phospholipid bilayer, where I've got two layers, that's what bilayer means, of these phospholipids. Phospho, I like water. Lipid, I don't like water. When I'm talking about the function of the plasma membrane of the cell, this is what acts as my barrier between the inside and the outside. This barrier does let some things through, no questions asked. You can go straight through the membrane. Do we have some ideas? Here, let's use our word from the other packet. Do we have some ideas about the biochemical properties? Let's use our technical word of things that can get through the membrane, that can get through. When I say biochemical properties, here's my hint for us over here. That's these four words right here. Hydrophilic, hydrophobic, polar, and nonpolar. What kinds of things can get through? Yeah, so I've got some ideas coming in the chat. Here's my question for you too. It's a corollary question to what I just asked. Which part of the plasma membrane do you have to match to be able to pass straight through? Is it the heads or the tails that you have to match to be able to sneak straight through that membrane? Yeah, we got to match those tails, right? We have to be the same as the tails because they're acting like the bouncer at a club, or they're acting like the security guard. They decide who does and does not get in. So those tails we saw from coloring our picture here, one of the things those tails are is they're hydrophobic. They don't like water. If you are a hydrophobic compound, you match those tails, you can sneak straight inside. The other thing we would say about those tails is that they are non-polar. If you are non-polar, those tails say you look just like me, go ahead and pass on through. So things that are hydrophobic, things that are non-polar, which means the same thing, right? It means that we don't play nice with water or we can't be around water. Those are the kind of things that if they're on one side of the membrane, they can go straight across to the other side of the membrane. or if they're here inside the cell, they can go straight through the membrane to get out of the cell. A big idea to make sure we write down for ourselves is that these tails that I find here in the very center of the plasma membrane, these tails are what decides what can get in and out of the cell. The head groups don't matter. Basically, the head groups are just there to protect the tails from the water that's on the inside or the outside. It's these tails that decide what can and cannot get in and out of the cell. So things that are hydrophobic, things that are nonpolar, they can sneak straight through. They go from outside to inside, no questions asked. Or they go from inside to outside, no questions asked. Remember, we had the example of respiration, the process of breathing, how oxygen and carbon dioxide, those are nonpolar things. So your cell's ability to get oxygen inside and its ability to get rid of carbon dioxide that it doesn't need anymore, it's because those compounds are nonpolar. It's because they can sneak straight in and straight out of a cell. They don't have to do anything special to do that. Here's my wink, wink, nudge, nudge for your studying. Somebody had mentioned in the chat, I keep having issues with figuring out what can and can't get through the membrane. All you need to do, you don't even need to care what the name of compounds are that I asked you about. All you're looking for on a question when it asks you if something could or could not get through the membrane, you're looking for these keywords. So maybe I'll give you the name of a compound, some special kind of fat, and I'll tell you that it's hydrophobic. You don't care about the name of the special kind of fat, you just care that it's hydrophobic. Or maybe I'll give you the name of a fancy kind of medicine, and I'll tell you that it's nonpolar. You don't care about the name of the medicine, you just care that it's nonpolar. Or you don't care if I tell you about some new kind of sugar, you care that I tell you that it's hydrophilic. Or you don't care that I tell you the name of a medication that is polar. All we care is that it's polar. When we're talking about what can and can't move across the membrane, the only things you're really looking for when you're working on those questions, you're looking for these keywords. Is it hydrophilic? Is it polar? Is it hydrophobic? Is it nonpolar? Those words will tell you. It doesn't matter what a compound is. Those words will tell you that it will or will not cross the membrane. The other keywords that you'll want to look for, you might see the words lipid soluble, lipid soluble. Lipid soluble means I dissolve in lipids. Hey, if I dissolve in lipids, do you think that I do or do not match them? If I dissolve in them, do you think I match them or I don't match them? If I completely surround myself in them. And here, let's give you the other word that you'd be looking for. Maybe that'll help us too. Water soluble. If something's water soluble, that means that it dissolves in water. Things that dissolve in water, those are things that do match water, right? Those were things that were polar or hydrophilic. Water soluble, I dissolve in water. That means that I'm polar or I'm hydrophilic or I have an ionic bond. So when we talk about lipid soluble, if I dissolve in lipids, I am going to match those lipids, which means that I'm going to be nonpolar or hydrophobic. Nonpolar or hydrophobic. So here's the other words we're looking for. Water soluble, lipid soluble. That tells me what I dissolve inside of. If I dissolve inside water, I match water. If I dissolve inside lipids, I match lipids. So if I have something that's lipid soluble, do we think that would or would not cross the plasma membrane? Would lipid soluble things be able to sneak straight through the membrane? Yes, yeah, they would. Lipid soluble things, because they're nonpolar, because they're hydrophobic, they can sneak straight inside. They're going straight from outside inside or inside to outside. If I tell you something is water soluble, though, that's not going to be able to sneak from outside to inside or from inside to outside. So keywords, like I said, it doesn't matter what I'm talking to you about, whether I'm talking to you about medicines, whether I'm talking to you about foods or vitamins. Really, you don't even care what I'm asking you, if it'll get inside or outside. You're looking for your keywords. Is it something that dissolves in water? Is it something that dissolves in fats? If I know what it dissolves in, that helps me to predict these words too. Hydrophobic and nonpolar, or hydrophilic and polar. We had a question in the chat about ions. When I talk about ions, Kai mentioned that ions are a thing that have a charge, right? Ions are something with a charge. If I have a charge, I am, let's see if we can help me out here. If I have a charge, I would or would not play nice with water. If I have a charge, I would or would not want to be surrounded by water. If I'm a sodium plus, Na plus, or a Cl minus. Yeah, so a couple of us have mentioned, if I have a charge, I do play nice with water. I want to be surrounded by water because water has those dipoles, those partial positives and partial negatives. I like those. That's what happens when you put salt in a cup of water. Remember, sodium and chloride split up from each other and they play nice with the water molecules in there. So if we say that we're talking about an ion is something with a charge, a negative or a positive charge. And it would play nice with water, which means it would not be able to cross the plasma membrane. So here's our big ideas with what can and cannot get across the membrane. Idea number one, we got to match what's going on in the middle of the membrane. We got to match those tails. So idea number two, the things that match those tails are things that are hydrophobic, things that are nonpolar, or we could also use the word lipid soluble. All of that means the same thing. Idea number three, if you are hydrophilic, if you are polar, if you are water soluble, or we can toss in there one other thing that your guided lesson mentioned. If you're really large, you also will not be able to cross the plasma membrane. So if you play nice with water, which means you're water soluble or hydrophilic or polar, that's a no-go. I'm not going to let you cross the membrane. And if you're particularly big, there's no way I'm going to let you squeeze through either. So the reason, the whole idea of lesson number 4 is let's talk about why I need to have proteins to help me transport some things into or out of the cell. And let's talk about why it's important for my concentrations of stuff inside to be different from my concentrations of stuff on the outside. How do we feel right now? Give me an emoji that shows me how we're feeling right now. I keep forgetting to give you guys penguins. Let me give you a penguin while I'm thinking of it. Got some thumbs up, got some betters. Dance party going on. That's awesome. Here comes our little penguin. He's going to wave at you. All right, there's your penguin for the day, because I keep forgetting. Okay. So, frame of reference for today's discussion. Everything we're talking about today and all the stuff that you're going to talk about through the rest of lesson number 4 that we'll talk about tomorrow is stuff that is hydrophilic. It's stuff that's polar. It's stuff that's water soluble. The idea with lesson number 4 is let's talk about all the things that can't just sneak in and out of my cell. Because if you can sneak in and out of the cell, I don't need to give you a special way to get in and out. You can do it on your own. You can go straight through. So let's talk about what happens if you can't go straight through in or out of the cell. That's the goal of lesson number 4. If I can't go in and out of the cell directly, I'm going to have to use a protein channel. Well, I'll just call them a protein for right now. I'm going to have to use a protein to make a special way to get things into my cell. So here's an important idea, and you have it in your pictures actually. Underline, highlight, star this right here on the picture. Lipid insoluble solutes. Lipid insoluble solutes. Lipid insoluble means I do not dissolve in lipids, means I don't match lipids. Important idea. If you match lipids, you don't need a protein to get inside the cell because you can sneak straight across the membrane. As we start talking about using proteins to move stuff into the cell, the only kind of things that need proteins to move into the cell are things that are lipid insoluble, or things that are hydrophilic, or things that are polar. They can't pass through, so I'm making them a special protein to allow them to do that. When I talk about my types of proteins that I can use to move things across the membrane, there are 2 big groups of proteins that I use. The first group of proteins that I use are called carrier proteins. Carrier proteins. Second group are called channel proteins. When I talk about carrier proteins, like I see over here on the left, these are proteins that change their shape. So you can see that here's image number 1 that shows me this process. Here's image number 2. So step 1, what happens? This little thing that I'm trying to take inside, it looks a lot like glucose to me. So I've got some glucose here on the outside of the cell. I want it to come into the cell. So step 1 is this sugar that I'm trying to get in attaches to my carrier protein, step 1. Step 2, carrier protein closes to the outside of the cell and opens to the inside of the cell, which is going to allow things to get into the cell. So a carrier protein starts open to the outside, closed to the inside, then it opens to the inside and closes to the outside. The big idea with carrier proteins is that carrier proteins change their shape. They change their shape to move things from outside to inside. It involves a shape change. When we talk about our channel proteins that move things across the membrane, the big idea with channel proteins is they have a channel, or they have an open space that never actually attaches to what they're moving. See, when we have this shape change over here, what happens is the protein attaches on one side to this sugar to move it, and then it changes its shape and detaches from what it was transporting. With a channel protein, I always have a channel, I always have a space for things to move through the protein. So a channel protein never attaches to what it transports. It never actually binds to what goes through this channel. Now, sometimes a channel protein might be, as we'll talk about here in a moment, what we call gated, meaning we don't always let this channel be open for things to get through. But with a channel protein, the biggest idea for us to remember on that is we're never going to attach to the thing that we're transporting. We always have a space for it to go through. I might have a security gate that's blocking it so that the molecules can't move through. But as soon as that gate moves, they go straight through this protein. I never actually attach to them. not like I attach to them over here when I have a carrier protein. So first type classification of the types of proteins that I use to move things: carrier proteins that will change their shape and attach to what they're transporting. Channel proteins that do not change their shape to transport something. They always have this channel, or they always have this space for things to move. Nicole asked the question, are the proteins always attached to the plasma membrane? Yes, these proteins that we're talking about, they always go from outside the plasma membrane to inside the plasma membrane. They're always going to go from one side to the other, because their goal is essentially to make a tunnel for things to go from one side to the other. Since they can't just go straight through the membrane, we have to make a tunnel that goes from one side to the other. Okay, her question is, are they always present? There are always some kinds of proteins in the membrane. Different cells will have different kinds of channels, or they'll have different kinds of carrier proteins in them. But yeah, pretty much every cell in your body is going to have some of these channels, or some of these carriers, because there's things like glucose that a cell needs to eat that can't go straight through the membrane. So I need to have a way to get it in. Or there are things like water that a cell needs to be balanced with the environment. Water is polar, so the easiest way to get that inside is by using these proteins. So all of your cells are going to have a mix of these types of proteins scattered throughout their membrane. Yeah, they're always present. So we had carrier proteins. Let me bounce back. My text will be gone, but here's my question for you. Carrier proteins over here, channel proteins over here. What do we think? Would a carrier protein or a channel protein, which of those do you think could transport things more quickly? What do we think might transport things more quickly? Yeah, so lots of us are voting in the chat, and we're correct. Channel proteins move things a lot more quickly than carrier proteins do. And it comes down to the fact that a channel protein, when it's open, things just pass straight through it. I don't have to do this whole attach to something and change my shape. Attach to something and change my shape. Carrier proteins take longer to move things than channel proteins do. Although, to be fair, carrier proteins are actually pretty darn fast too. But when we're thinking about the shape of things having to change with a carrier protein compared to a channel protein where the shape doesn't have to change, things can go a lot faster. Yeah, so Hannah's mentioning, like you had in your guided lesson, think about a channel protein kind of like a garden or a hose that you'd use to put out a fire. Lots of stuff can just go straight through it. With a carrier protein, we've got to open and shut, shut. Stuff's not constantly moving through like it would be with a channel protein. When we talk about channel proteins, there are two kinds of channel proteins. So for my friends who've had a chance to work on the lesson, what's the name of the kind of channel proteins that are always open? Which kind of channel proteins are always open? Do you remember those? Yeah, so channel proteins that are always open are called leakage channels. Leakage channels. Think about leakage channels like a leaky faucet that's always dripping. So leakage channels are always open, always open. So they have this space, this channel for stuff to pass through. Got nothing that blocks the top or the bottom of this channel. So stuff is always going to move through it. I'm always going to move my stuff from where it's a high concentration to where it's a low concentration. A leakage channel is always open and it's always moving things. My other types of channel proteins that I have in the body though, or on the cells, they're called gated channels, gated channels, and gated channels are still a channel. We still don't have to attach to what we're moving, but with gated channels, help me out in the chat, they are or are not always open. Gated channels are or are not always open. Yeah, gated channels are not always open. Gated channels are not always open. The deal with a gated channel is I need to open it somehow to help me allow things to pass through. When my gate opens up this channel, stuff can move, no problem. But until I've opened that gate, stuff can't get through. 3 kinds of gated channels that we need to know about. And when we talk about these types of gated channels, use their name to figure out what opens up the gate. So here, let's do an easy one together. The first type of gated channel that you see in the middle is called a chemically gated channel. I promise this is not a trick question. What opens a chemically gated channel? What's going to open my gate if it's a chemically gated channel? Yeah, Hannah put in the chat, chemicals, LOL. Yep, chemicals, it's right. Dr. Hollis may ask some mean questions, but I promise this is not a mean one. It's not a confusing one. Chemically gated channels open with chemicals. So the most common chemical that we're going to see when we talk about chemically gated channels are neurotransmitters. These are the type of chemicals that neurons use to talk to each other. So the way this works is I have a chemically gated channel protein over here. Notice how it's closed right now. There's no space for things to go through. When my chemical binds, so when I send a neurotransmitter message from one cell to another, that neurotransmitter message, it acts like a key. It goes into this part of my gated channel. When I attach that chemical to this gated channel, that gate opens up, and now I've got a channel for things to rush in and rush out of. So a chemically gated channel is a channel that is not always open. That's what gated means. The way that I get it open is by using chemicals. I have a chemical key that opens up the gate. When I open the gate, now I've got this channel that things just pass straight through. I don't attach to them. I don't have to open on one side and then close on the other. A chemically gated channel, whenever that chemical attaches, I can rush stuff in or out. Nicole asked if things could move both ways at the same time. Depending on the shape of the channel protein, they could. You'll notice this particular channel protein both transports sodium ions and also potassium ions. So chemically gated channels might transport more than one thing. They could move either direction depending on what they're transporting. Yeah. So chemically gated channel. Chemically gated, I used a chemical to open it up. My second type of channel that I see over on the right is called a voltage gated channel. A voltage gated channel. And when we talk about voltage gated, voltage should make you think of charges, as in electricity. A voltage gated channel opens up when the charge on the plasma membrane changes. So we've got our 2 states of this particular gated channel here. We have our state when this channel is closed, and we have our state when this channel is open. So notice at the bottom, the channel is closed, and so the top image, we're closed right here, and in the bottom image, we're open. When I think about the cells in my body, the cells in my body are actually more negative on the inside than they are on the outside. Let's see if we can remember. Here's an important word. When I talk about a cell that has a different charge on the inside compared to the outside, what's the name or what's the word that I use if a cell has a different charge on the inside compared to the outside? Yeah, Jacqueline chimed in for us. Yeah, she's questioning herself. Don't question, you're right. When a cell has a different charge inside and outside, we call that cell polarized. Polarized. Here is the reason that I need my cell to be polarized. The reason I need my cell to be polarized, have a different charge inside and outside, is because inside the membrane of my cells, I've got a whole bunch of voltage gated channels. As in, the way I open the gate is I change the charge on my plasma membrane. So in normal situations, when my cell is polarized, when things are different on the inside compared to the outside, lots of these channels are closed. If my cell, here's the word we talked about before, if my cell becomes depolarized, meaning it loses that difference in charge from the inside compared to the outside, or as we're going to see with neurons at the end of lesson number 4, it actually changes it. It makes it positive inside and negative outside. Now it's opposite of normal. If my neuron is depolarized, or if my neuron changes its charge, its voltage, that's going to open up these channels. And when these channels open up, stuff can rush in or stuff can rush out, depending on what this particular channel it actually transports. So voltage-gated channels open up when the charge changes. Chemically gated channels open up when a chemical attaches. Either way, with both of these types of gated channels, when they open up, stuff can go in or stuff can go out, depending on what we're trying to transport here. The last kind of channel that we have is called a mechanically gated channel. Mechanically gated channel. Mechanically gated channels are a lot like the kind of gate you think of normally when you think of a gate on a fence or a gate to a backyard. In a mechanically gated channel, what opens up these channel proteins is when we physically press on them. So we apply some kind of pressure to physically change their shape, or we physically press open the gate. It's something that your physics class will call mechanical energy when you're physically pushing on something. So the final way that I can open up my channel protein is by pressing on the membrane or pressing on the protein. When something bumps into it, it opens up. Otherwise, when nothing's bumping, it's closed for us. So mechanically gated channels, we push them. Voltage gated channels, we change the charge on the membrane. Chemically gated channels, we use a chemical key to get them open. Leakage channels, by the way, remember, they're always open, so I don't have to do anything. These guys are always going to transport stuff in or out. Let's see if we happen to remember, though, from that guided lesson, leakage channels or gated channels. Who transports stuff faster? Is it leakage channels or gated channels that move stuff faster? A couple of us have chimed in correctly. Gated channels move stuff faster. Gated channels, and here's where we can get some more analogies in here. Gated channels are like a fire hose. So when they turn on that gated channel, when a fire hose is on, all the water rushes out of it. When it's off, there's nothing moving through. So gated channels are kind of like a fire hose. Leakage channels are like the example that I mentioned before. That's a leaky faucet. A leaky faucet. They're always transporting stuff, but they're always transporting it really slowly. Water is dripping out of this faucet. Compared to a gated channel, when you open it up, we've got a fire hose. All the stuff is going to rush through. So things move more quickly through a gated channel than they do through a leakage channel. How do we feel about our types of channel proteins? Or what questions do we have about channel proteins? I do see a question from Nicole that I missed, that she asked if things can sneak in or out with these channels. I'll just mention that the channels opening up are a little bit more purposeful. Their chemistry will only let them move certain things. And so it's not like I'm typically going to open up a channel and just lose stuff randomly. They're going to be, their shape is only going to allow them to transport certain things. So we don't have a lot of accidental sneaking, put it that way. It's more purposeful sneaking. Okay, let me look and see. I am going to save the specifics of this particular analogy for you guys when you're doing a guided lesson together. But hey, who doesn't love looking at pictures of golden retriever puppies, right? So this was a fun little web search for me to do to find these pictures. One of the ways that I wanted you guys to think about the difference between gated channels versus leakage channels was to think about having a bunch of puppies in your backyard. So whether those puppies stay in your backyard or find a way to escape, that's what that analogy talks about. So if those puppies are leaving one by one, they're kind of leaking out of your backyard. That would be what a leakage channel does, versus when you come home and you open up that gate, all those puppies run out and be free. That's more of those gated channels for us. So make sure to check out that puppies analogy. Also make sure to check out the analogy about the different kind of gates you could have on your backyard, because that'll talk to you about voltage gated, mechanically gated, chemically gated, that kind of stuff. So just some other ways to think about the kinds of transport proteins we have, and also the ways that we open up those proteins. What I want to, let me check really fast. Okay, I have just a couple more ideas that I want to talk with you guys about. This little thing is fun. I have no idea why it ate my arrow. What we're talking about here, let me add those arrows back. When we talk about either our leakage channel proteins or our gated channel proteins, when we talk about either of these types of proteins, we are doing something called facilitated diffusion. Facilitated diffusion. When we think about facilitated diffusion, here's a couple of things we should know. First part of its word, facilitated. Think of facilitated meaning that we have a facilitator, meaning that's someone that makes things happen. That's what a facilitator is. So when I talk about facilitated diffusion, I mean that I use a protein to facilitate or to make happen the process of diffusion. Facilitated diffusion is a special kind of diffusion that I use a protein to make happen. So let's look at our questions together here. We're doing facilitated diffusion, meaning I'm still doing diffusion. When we talked about normal diffusion, which way were things moving? Were they moving from low concentration to high concentration, or high concentration to low concentration? When I do diffusion, which way do things move? couple of us are scared to vote. I promise that it is as simple as you think. Diffusion is when we go from high to low. From high to low, diffusion. If we're going from high concentration to low concentration, does that take energy to go from high concentration to low concentration? Yeah, no energy required. No energy required. Remember the example way back in like lesson number 2 that we talked about with diffusion is if we walked into a room, we can pretend we're at the grocery store, right? This is actually a fitting example right now in the time of COVID. We go to the grocery store. The grocery store has, we'll say it's a small one. It's only got 10 aisles, really small. And we've got 10 people that are shopping at that grocery store. The process of diffusion would be we all somehow start in aisle number 1 and we end up spreading out into aisles number 1 through 10. We go from high concentration, everyone together, to low concentration, where we're all spread out. And all of us, our blood pressure is a lot lower because now thinking that somebody's going to infect us with COVID, right? So it takes no energy for us to spread out from each other. We don't have to be worried about bumping into each other when we go from having 10 of us in one row to spreading out, high concentration to low concentration. If I don't use energy to move something, what kind of transport do I call that? If there's no energy required to do that, what do I call that kind of transport? Yeah, Nicole is chiming in. She's right. If there's no energy required, that is an example of passive transport. Passive transport. No energy required. Okay, so here's a big important idea, and it's so big and important I'm going to type it. Let's make sure we write this down, underline, highlight, star it. When I use gated channel, actually here, I'm just going to say when I use channel proteins to transport things across the plasma membrane, I am doing passive transport. I am doing passive transport. This is an underline, highlight, star idea. We need to make sure we know this. When I use a voltage gated channel, I'm doing passive transport. When I use a leakage channel, I'm doing passive transport. When I use a mechanically gated channel, I'm doing passive transport. Anytime I use a channel protein, doesn't matter which kind of channel protein. We talked about the types, right? It doesn't matter which kind of channel protein I'm using, I am always doing passive transport. So that means I am always going from high concentration to low concentration. That's the only way that I can move things when I'm doing facilitated diffusion. When I use these channel proteins, they only ever let stuff go from high concentration to low concentration. Yeah, so Jacqueline asked in the chat, so facilitated diffusion is the exact same as regular diffusion. Yes, 100%. You get the star for that's the big idea that we wanted to know. 100% true. Facilitated diffusion is exactly the same as regular diffusion, except for the fact that I use a protein. That's the only difference between facilitated diffusion and regular diffusion. The only difference, I'm still going from high to low. I'm still doing passive transport. The only difference is that I have to use a protein to make it happen. Otherwise, it's exactly the same. I just have to use a protein. Because, here's our reminders, because what I'm moving is an ion, it has a charge, or because what I'm moving is polar, or because what I'm moving is hydrophilic. Because I'm moving something that doesn't play nice with the middle of the plasma membrane, I use a protein to make it get through. That's facilitated diffusion. I go from high to low using a protein. Thumbs up, thumbs down. What do we think about facilitated diffusion? Those channel proteins. Or what questions do we have? Good. Okay, looks like we're feeling a little bit better. Two things I want to mention, and then I'm going to call it a day for our class, and then stick around for questions you guys have. When we talk about the inside and the outside of a cell, when we talk about intracellular fluid, that's our cytosol, and we compare that to extracellular fluids like interstitial fluid, like plasma. When we talk about these types of fluid, and we did this statement together. Remember, we fixed the statement that said the recipe for intracellular fluid and extracellular fluid is the same. Remember how we fixed that statement together with our groups? What we have inside the cell is not the same as what we have outside the cell. So if things are not the same inside versus outside, here's what we got to consider. When I have a high concentration somewhere, diffusion wants to take us from having a high concentration and a low concentration, having two different concentrations. The goal of diffusion is to make things isotonic. Here's that word back again. What did isotonic mean? What is isotonic? That concentration word. Yeah, iso means equal. Iso means equal or the same. Okay. Inside the cell and outside the cell, it is not the same, right? We fixed this statement. We said it's not the same. We can look at our graph here and we can see how it's not the same. We can see that there's different amounts of sodium, different amounts of chloride, different amounts of potassium. That's the ones that we focused on. The inside and the outside of a cell is not the same. But remember that the goal of diffusion was to make things the same. Diffusion, we've got two solutions, one that's really high in sodium, one that's really low. Diffusion says, oh, I can fix that. I can make them equal. Or again, I've got one solution that's really high in potassium and one that's really low. Diffusion says, I can fix that. Facilitated diffusion, just like regular diffusion, its goal is to make things isotonic. So here, the goal of facilitated diffusion, just like regular diffusion, is isotonic solutions. There's that phrase back from earlier in the semester. The goal of facilitated diffusion is isotonic solutions. If I let my transport proteins do the process of facilitated diffusion without stopping them, without checking them, I would end up with isotonic solutions. I would end up with solutions that are equal or that are the same. Here comes that word that we said before earlier in class today. What do I call it when the charge is different inside versus outside? What do I call it when we're different inside compared to outside? Yeah, that word is back again, right? It's called polarized. When a cell is different inside and outside, it's polarized. Cells need to stay polarized to be alive. Remember, that's what we said. We've got to keep things different inside versus outside for a cell to be alive. Channel proteins do facilitated diffusion. If my channel proteins were not gated, hey, remind me, this word gated, does that mean we are or are not always open? If I've got a gated protein, it is or is not always open. Yeah, a couple of us have chimed in. Not a trick question. Gated proteins are not always open. I got to open that gate for them to move stuff. If I have a gate, which essentially decides whether or not I move stuff, I can keep things different. Because if my channel protein is not gated, if my channel protein is always open, I am always doing facilitated diffusion. I am always moving things from high concentration to low concentration. From high to low, from high to low. I do enough of that, moving things from high to low, that I end up isotonic. I end up the same. So I need to have gated channel proteins, that is, proteins that are not always open, to make sure that a cell stays polarized. So why do I need gated channel proteins? Because gated channel proteins make sure that the inside and the outside can stay different. It makes sure that we don't end up isotonic. I only move stuff when I want to, and when I want to is when I open up those gates. Yeah, so Tierney mentioned the idea of monitoring what comes in and out. That's another great way to think about it. Absolutely. I want to make sure that stuff's not always moving. If I don't have gates, stuff always moves and my cell stops being polarized. So I need gated channels to regulate or to control what moves in and out, or maybe when things move in or out. That's the job of these gated channel proteins, to make sure I don't always do facilitated diffusion. Because if I always do it, that cell is not going to be polarized. It's going to be dead. I need to have those gated proteins to decide when I open and close. I know that we did not get to active transport today, but we're about out of time for our regular class session. Tomorrow we will dive right in with active transport, and then we'll talk about how active transport and passive transport are seen when we look at the way that neurons normally do their job. Before I call it a wrap for our class session, do we have any other particular questions about these things that we've talked about today? Are we feeling a little better about some of this stuff from lesson number 4? How are we feeling now? Tierney says she's feeling much better. Excellent. Yeah, so Michaela's asking about the test. Yes, for the lecture test, you're going to use the lecture resources. So the lecture outlines. The big thing that I keep referring students to is, if you look at the top of each of your lecture outlines, there's a thing called the learning objectives. The learning objectives is basically your study guide. It's what I expect you to be able to do after you have studied the material and learned it to the extent that you need to. So check out those learning objectives because some of those learning objectives say that we need to memorize, like list something. If we need to list something, that's just memorizing. So it would say like list the recipes for the fluid that's inside and outside the cell. That literally means I would ask you a question where, is there more sodium inside or outside? It's a basic question. Some of those learning objectives will say to explain something, like explain how anatomy is related to physiology. If you see the word explain, that means I'm more likely to ask you to use that information. So don't just memorize something if you've got an explain learning objective, because I'm going to ask you for more details with those explain learning objectives or describe learning objectives. So check those out to get an idea of what information you just have to memorize and what information maybe you should practice standing in front of your mirror, explaining it to yourself out loud. It feels really awkward, but I tell students all the time, stand in front of your mirror, try to explain an idea to yourself. If you can't explain it to yourself, then maybe we need to study it a little bit more to make sure we understand it best. Let's see. So Jacqueline asked if sodium is always concentrated on the inside or the outside. Yes. So this graph here is similar to what you looked at in lesson number 2. 100% make sure that we remember our salty banana. That's my hint for you. The salty banana was how we remembered what's more concentrated inside versus outside. That is always true. There's only a couple of exceptions to that in the we will talk about one of them at the very end of the semester. But I want you to assume for 90% of the semester that there's more sodium and chloride outside and more potassium inside. A couple of questions about brown fat versus white fat, as well as I'll toss in there water intoxication. The 2 articles that we read this unit for lesson number 1 and number 2 are included on the test. So do not forget about them. They are included on that test. So make sure you'll notice in the lesson number 1 and the lesson number 2 folders, you'll notice that there are a list of learning objectives for those 2 articles as well. So that'll help you to know what you were supposed to learn from those articles too. Yeah, Michaela says she's been explaining concepts to her siblings, so they're going to know AMP by the end. That's perfect. I recommend that. I apologize, guys. My daughter is dying. Yeah, so explaining to siblings, explaining to classmates, explaining to yourself, whoever you want to try to talk things out with, that's perfect. That's a great way to study. Any other last minute questions? And again, I apologize. My daughter is having a 3-year-old moment. Michaela asked if the SI sessions are recorded. I don't know. That's a really great question. I will get in touch with Elise to ask her about that. Let me make a note for myself to do that. Elise, okay, so Nicole said that Elise said they are not. Okay. So I'm glad that we have an answer to that question. Looks like they're not. I know she's hosting a session on Friday. So if you can, try to make it into that session on Friday. And Nicole says she does post the slides that she uses. So yeah, definitely try to make it to those sessions, but at least try to reference those slides that she posts. For my friends that are attending those sessions, is it correct that she posts them on her landing page? Does that sound right, that she posts them there on that link that we have? Okay, so if you check out on the Start Here area of our course site, it takes you to her landing page. and there should be a place that says slides from recent sessions or something like that. All right, well, I think I'm gonna turn off my mic because, like I said, my daughter's dying. I so apologize for that. The joys of COVID, right? Working from home. So I'm gonna go ahead and turn off my mic. I will stick around in questions, and if there's stuff you want to talk with me about, I'm officially gonna do office hours now until about 1 o'clock. I'll stick around if you have more questions. That's fine. I'm gonna go ahead and end my recording though, and we'll call it a day. So hope to see you guys tomorrow at 9:30. We will keep talking about stuff from lesson number 4.